Hello everyone, and welcome to the first in our series about teaching maths in the FET phase, that is grades 10, 11 and 12. This series is aimed at maths teachers in the FET phase and everyone else who's interested in education in South Africa. Let's start by taking a look at our video looking at today's topic. Euclidean geometry seems to deal with perfection. The concepts and consequences of Euclidean geometry are all built up from ideas of a perfect point, perfect straight lines, and perfect circles. But Greek geometry was also understood to describe the space humans live in. Although since the 19th century this view has been challenged, on an everyday basis, Euclidean geometry is still applicable. In fact, problems from many fields can be solved more easily when they are represented geometrically. Take archaeology, for instance. This archaeologist has found the remains of 4 columns in the temple ruin she's excavating. She hypothesizes that these columns were part of a circular temple. If she can prove that the columns are concyclic, that is, they lie on the circumference of a circle, she will have a clear idea where to continue her excavations. She draws an accurate diagram representing the 4 columns. She then connects the points and measures the angles at A and at B. If she can show that the 2 angles are equal, then she knows the 4 columns lie on a circle, as according to the theorem, if a line segment subtends equal angles on the same side of it, then the 4 points are concyclic. She finds that the angles are equal, thus proving that the 4 points are concyclic. In the classroom too, learners can learn about geometry through using real-life problems. In this way, their traditionally negative attitude to the subject can be overcome.
I think that geometry is difficult. Even if you give them work, some don't attempt to write that work. They just say it's difficult. And I think they've taken that from standard 6.
The most important thing, in my view, for teachers to teach in an exploratory way, rather than the old way of teaching theorems and applying riders, is the exploratory way. It works exactly with how geometry was essentially discovered. The discoverers of geometry did not really learn it from somewhere. They saw these things happening practically. And that's where we need to take our children back to, so that they can also be young discoverers, young explorers.
The intended outcomes for learners in the lesson are to understand that all points on the circumference of a circle are equidistant from its center, to use problem solving and investigation to become familiar with certain concepts in circle geometry, to learn that the line through the center of a circle and the midpoint of a chord is perpendicular to the chord. First, the teacher, Jabulile Mkhonza of Pafokgang Secondary School in Soweto, sets the problem for her class.
You have a rectangle piece of wood with 40 centimeter by 60 centimeter, and you need to design a shelf to fit in a corner. Are you having a picture of that? Yes. To attempt this activity, try to draw a circle that is going to pass through this point and this point.
The teacher has divided the class into groups of 4. Allowing the learners to work in groups gives them the chance to bounce ideas off each other. It can help make the problem less intimidating.
Learners in a group, they see things differently. And when they discover these things, they start to translate into better meaning than when a teacher stands in front of the chalkboard and tells them which angle is equals to whatever angle, or which triangle is congruent to whatever triangle.
The teacher moves around the classroom, assisting learners where necessary.
You must draw a circle that's going to pass through point A and C.
The learners try various approaches. Some take the compass and try out different centers for the circle and different radii. Other learners take a shortcut and just use the protractor.
I think it's the right approach because the learners find for themselves. You don't spoon feed them.
Representatives from two groups present their solutions to the class.
And take the other one. It makes
The teacher points out where there are limitations to the approach.
Will this work for a bigger rectangle?
The learner points out that if the rectangle was bigger, the protractor would not reach both corners.
Yeah, I just use only a compass and a ruler and a pencil.
The learner extends the shorter line to make it the same length as the longer line and uses the end of the extended line as a center point.
2 here. It didn't, even in my answer sheet, it didn't work very properly, but I tried like this.
You find that the first one did work for this small rectangle. The second one didn't pass exactly to the second point.
As none of the learners have come up with a satisfactory solution, the teacher demonstrates how to solve the problem, placing the compass point on A and C and drawing two arcs that intersect. Using this point as a center, she then draws a circle that passes through the 2 points.
Where they meet.
She then asks the learners to practice doing what she has just shown them. This activity helps them gain confidence with using the compass.
But it's no longer a circle.
Sorry, Pauline, before you do anything, you don't adjust this. Once you have started with this distance,
yes, I use it.
you don't adjust it for the second point.
Once the learners have shown they are confident enough to do the activity correctly, the teacher sets them another task.
Do you see the curved part AC?
Yes.
What do you call that?
An arc.
Try to draw more arcs, that is curved parts from A to C.
We can't make it small.
Initially, some of the learners try to draw different arcs using the same center point.
Why are you using one circle? Because if you use one circle, look at this is one and the same arc. Try to change the distance between the compass.
The learners soon realize that by adjusting the initial radius on their compass, they can create a variety of center points and a variety of different arcs. The teacher then reminds them of the original problem they are trying to solve.
Look at the arcs that you have. Are they all suitable for the curve of the wooden block, of the shelf that you're going to design? Do you think this arc is it suitable for designing the shelf?
No, of course.
Why?
It's out of the rectangle, I mean.
The arc the learner is referring to passes partly outside the rectangle, and consequently the shelf would only be partly circular if it were used.
Let's look at the centers. What do you notice about the centers? Itumeleng?
They form a straight line. They follow behind each other, miss.
The teacher asks the learners to draw a line through the centers and extend it through the rectangle.
Then you try to notice what is this straight line doing to the rectangle? You note it down. And what does this straight line do to the arcs that you have drawn?
The learners discuss the question in their groups.
The straight line divides the arc into 2 equal parts and the rectangle.
How?
If you take your ruler and measure,
It will be 1.5.
and then measure the size, 1.5, right?
Then
It's the same. And from here, 4.3, 4.3, it's the same. It divides them into 2 equal parts.
The advantages is that the hypotheses, which are usually given to the students, could be made by the students themselves. And this will bring the geometry closer to them. As it stands, when the teacher gives them a hypothesis, which they are then expected to prove, it's already formed. The excitement comes. The excitement in mathematics is in the intuition, is in the forming of hypotheses, is in the creativity in making connections which were not there before.
Okay, you have said this line divides the rectangle into 2 equal parts. It's okay. Then, what about the arcs? Try to look at the arcs.
They form the straight line.
no.
Try to look at one arc and see what is the straight line doing to that arc. let's look at the straight line with relation to the arc. What is it doing to the arc?
Okay, it divides the arcs into two parts or sides.
It just cuts the arc anyway.
The teacher guides the learners to state more accurately that the line bisects the arc.
Okay, let's look at the rectangular block. What is the straight line doing to the rectangular block?
It divides the rectangle into two equal parts.
The teacher then asks the learners to draw the diagonal of the rectangle from point A to point C.
Let's look at that line in relation to the arc. What do you call that line? Mandla?
It's the chord.
Thank you, Mandla. Try to measure the angle between that straight line and the chord. How many degrees did you get there? 9. Thank you, learners. You have demonstrated the theorem that says that if a line is drawn from the center of the circle to the midpoint of a chord, then that line is perpendicular to the chord. Are we together? Yes. Then let's recap what we have done today.
The teacher recaps the main steps the class has moved through during the lesson in order to reach this conclusion.
Thank you, class. Tomorrow we look at the formal proof of this theorem. Like today, we were busy with the shelf only to find that you are learning theorems. We've demonstrated a theorem. The kids were not aware that you are going to demonstrate a theorem.
It was fun. I did geometry from standard 5, but this one was amazing.
That's what we normally don't do. You do things on your own. So when you kind of like do it with other people, it's kind of like fun because you share ideas, unlike doing it alone.
Jabulile believes she has largely achieved all the intended outcomes, though some reinforcement of them may be necessary in the lessons that follow. Learners will also need formal proof of the chord theorem and other hypotheses developed during the lesson.
The new approach of investigation is bound to change the attitude towards geometry because they have a chance of hands-on. The minute a person is doing practicals, is handling these things with his own hands, is bound to have interest of what he's doing.
In geometry, you can have abstract ideas built on physical entities, and that physicality is very important.
Now that we've seen the video, let's welcome our guests for this session. Meira Hockman from the School of Maths at Wits University, Edward Museki from NGO Protech, and Catherine Hunter, who's an independent maths education consultant. And looking back at the video, we saw the teacher say many learners have major problems with geometry. Why is this? Meira?
I presume it's in contrast with a minor problem that might arise in algebra. One point that I could highlight among many, I think, is that in algebra there are set algorithms which students feel comfortable in using. While in geometry, the set algorithms don't exist. The ideas are based on building axioms, on theorems, and on proof. And that is quite hard.
Edward, would you agree?
Yeah, I do agree. And the other problem with perhaps geometry is that you've got, as Meira said, you have a string of things, a string of theorems that you've got to put together. And when you get to a rider, for instance, a learner has to see those theorems coming out, and it becomes difficult. As opposed to algebra, where you simply follow algorithms as you go.
Catherine?
Often we don't provide learners with sufficient opportunity to explore spatial issues, to see problems pictorially, to see diagrams, and to be able to interpret those in a way that is going to be the blocks on which they will build the FET algorithms. And I think that is something that all teachers should actually bear in mind, is give learners ample opportunity to explore problems, whether they be the geometry or algebra, to allow them to explore their own way of doing things visually, so that they can interact with a spatial interpretation on the page. And that will give them a huge window into being able to interpret the diagrams that they're faced with when they do these problems.
Catherine, what do you think is different about the way this lesson has been taught as opposed to other lessons?
Oh, there's so many ways. I thought it was a superb lesson. The main point being the fact that it was creative and that it was practical. The teacher started with a very practical problem that she presented to the learners, that they had to build a shelf of a particular shape and so on. And then she went from there into more abstract thought. They used mathematical instruments along the way. They were given the opportunity with each other in small groups, only four, so everybody would have an opportunity to try those mathematical instruments, to explore what they had to do, as opposed to watching the educator, the teacher, stand at the board and demonstrate how to do it. So they have to take responsibility for their own learning. They know that there is a chance that they will be called to the board to demonstrate what they would have to do, and they need to be able to explain it. So there's a much greater chance that the learners will actually internalize the logic and the learning that comes along with the experience, as opposed to watching and just having to pick things up in that way.
Mara, from what you saw?
A discovery approach puts the learner in direct touch with the concepts. For example, words which might have no meaning to the students become meaningful when they're directly involved with constructing, say, radii or arcs, or rectangles or circles. So while the emphasis in this lesson was on creativity, the understandings that were reached were those of these basic concepts: radii, arcs, area, rectangles, length, breadth. However, the danger that one has to look at is that one is building on those concepts. So those are the concepts that are going to be understood through the experiment, through the investigation. However, the end point, the theorem that comes out, must also be fully understood, because the next interaction is going to build on that. So the discovery approach is excellent, but then the consolidation exercise is just as important.
Edward, do you also think the positive aspects of the discovery approach for teaching geometry are?
Yeah. What is critical about it is that learners construct their own definition, if you want to, and their own understanding of what an arc is. They are there, they can define the arc because they have drawn the arc. They could define, even though they may not know the name to that particular thing. Like they drew an arc, probably they did not know what an arc is. They could define what they are looking at. And then maybe the educator can then come and put a name to it.
Catherine, do you think there are any dangers in using discovery approach shown in this lesson?
I don't know that about seen in this lesson, but I would absolutely agree with the point already made that you have to consolidate it and make sure that the learners in fact have grasped the main points that they were intended to grasp. Right. It's all very well building on prior knowledge, which of course group work allows them to do, develop verbal skills that match the visual skills that match the understanding and the concept and knowledge development. But at the end of the lesson, the teacher does need to be sure that the learners are ready to move on to the next lesson. And that has implications, by the way, for time management. And I think that's very well demonstrated in this particular video, in that you cannot have the bell go when you're mid-sentence and midstream. The educator has to keep an eye on her watch and be sure that even if she has to cut an activity in half and continue it in a later lesson, she does need to spend those last few minutes consolidating what has already been learnt so that there is no time lost.
Mara, looking at the dangers that have been mentioned by Catherine and Edward, any others?
Students pick up very quickly on what do they need to emphasize, and the emphasis comes from the test or the exam. And unfortunately, it's very difficult to test skills of discovery learning in the exam situation. So the student will pick up quickly that while we discovered the theorem in the lecture, ultimately we need to learn the theorem. And the dangers come in that learning situation. So one has to distinguish between at what point you start learning by heart, learning by rote. However, that rote learning must follow the understanding of the basic principles.
Edward, any other issues arising from the video that you'd like to raise?
It would be very interesting how the learners are going to learn the theorem, the actual theorem, and the proof of the theorem. moving from having discovered that the lines are perpendicular when you draw the center from the circle. You know, there's a situation what one would want to see.
Okay, Catherine, what do you have to? Do you have any issues that you'd like to raise?
What I thought was quite interesting was that this teacher has obviously won the trust and the faith of the learners.
Right.
And you can see that in the sense that they do get on with their work. They're not trying to sort of take advantage of the fact that they're left alone to work. She can only handle one group at a time, so she walks around seeing the different groups. And they obviously have a tradition and a background that allows them to know that they are in good hands, and that the learning that arises out of their discussion is going to be taken forward in the direction that it should go.
Mera, any issues that you'd like to raise?
The ideas of dividing, when you divide a line or you divide the rectangle, you know, into equal parts, what in fact is divided equally? The ideas of areas being equal or lengths being equal, these are basic concepts which the teacher could have explored at the same time and taken the opportunity to explain that when an arc is divided, it's quite different to when the rectangle is divided, and what does she mean by the rectangle being equally divided. So these are things that the experienced teacher should have in mind and take the opportunity further explore during the session as well.
Thank you very much for joining us for this session. And that is it for this session. Please keep your eyes open for episode 2 coming up soon. Thank you for watching and goodbye.